Hi everyone, my name is Monique Casanova and welcome to What's the Scope? This is a student initiative hosted by Eastern Engineering Group where students get to pick out a structure and we contact a design team to see if they are willing to answer our technical and design questions. Today we are launching our podcast, so now you can listen to all of our interviews on Spotify. You can look us up by What's the Scope by Eastern Engineering Group. Or if you are listening to the podcast right now, you can go to our YouTube channel and you can watch the videos and get to see all the professionals. You can see all the pictures they share with us. It's very cool. Today, we are very excited because we are going to be talking about an air traffic control tower at the Melbourne International Airport in Orlando. Not only is it super interesting to listen about these aviation projects, but we were actually part of the team that CTBX Aviation put together. So the structural engineers from Eastern Engineering were working on this project. We are very excited about today's interview. You shouldn't miss it. Check it out. All right. So now that we're all together, welcome Brian, welcome Alexis. This is David. Thank you so much for taking the time out of your day to answering our questions. David, today we will be interviewing Brian Lally. He is the president of CTBX Aviation. This is a firm that specializes in the planning, design, and construction administration of control towers and other airport buildings. Brian has completed over 70 control towers in the United States, and he is an FAA licensed private pilot. We will be also speaking with Alexis Martinez, the director of our structural engineering department here at Eastern Engineering Group. And for those who don't know, we are a structural engineering firm located here in Miami. David, do you want to give a little introduction of yourself, please?
Yeah, I'm David Manosalva, and I'm a senior at FIU currently, expected graduation around December, on December. I was part of the ASCE at FIU. I was conference director for 2019-2020, and my passion is structural engineering. I would love to become a structural engineer, and this opportunity is very amazing to me. So thank you guys for being here. I always tell my friends or people that ask me, "Oh, what do you want to do? What's your goals?" And I'm like, I would love to be part of designing an airport. That's my biggest dream. So that's why I chose these structures, like the air traffic control tower. So we could go ahead with asking these questions. We'll start off with Brian. How long was the design phase regarding the air traffic control tower, and how long was the construction phase?
Okay, well, first let me tell you what we designed. We designed an 8-story building with a 25 by 25 foot footprint, so about 625 square feet, and that translates to each floor. If you subtract out the stairwell, there's about 400 square feet of usable space on each floor. Plus over 500 square feet up in the control cab because you don't have that big stairwell up there. It included 2 air traffic control equipment rooms with all the electronics, the recorders and radios and backups. It also had an air traffic manager's office, a break room, conference room, and training area. So it took about 6 months to design all that. We were lucky that we got some good, quick FAA reviews. Normally, they take their time, and they can't be too careful. But This time we had some good reviewers. We had some reviewers that were familiar with our designs from past projects. So it went fairly quickly. And then the construction phase began about 3 months after the design was completed. It was done under a construction manager at risk type contract with a local contractor here, and they completed it in about 18 months. Now that might sound, I don't know if that sounds like a long time or a short time to you, but
That sounds long.
it sounds like, to me, it sounds like a little bit of a long time for that size of a building, but there's a lot of trades that have to work in those small spaces. I mentioned before, there's 400 square feet on
Right.
usable area each floor. So you can imagine you get plumbers, electricians, and whatnot in there, all kinds of people, but they all can't be in there at one time. So they've got to strategically schedule each trade in and out of there so they're not literally bumping into each other. So it takes a little bit longer.
That makes sense.
Yeah.
That makes a lot of sense. Wow. Didn't think about that aspect of it. So it took 6 months for the design, 3 months for construction, and then, or 18 months? 3?
18
You said
months,
3?
3 months for a bidding phase, putting it out in the
Okay.
street, contracting, and then 18 months once they started construction. Yeah.
Okay. That makes sense. Okay. Perfect. Another question would be, was the existing, I read that it was obsolete, the old air traffic control tower. Was it actually obsolete? And what was the goal for the new design?
Yeah. Well, FAA is always good at working around obsolescence to maintain safety. And they were doing that here. It wasn't an unsafe facility as far as directing traffic. But as far as the building, having leaks and, sometimes with electrical problems and just basically being old, it was over 50 years old. It was time to build a new tower. It also, in the last 50 years, FAA has changed their height requirements a couple of times. So it was drastically too short by today's standards. Plus the airport, I think, had extended their runway at least one time during that period. So the new tower is about twice as tall as the old tower. So that was a major, most obvious benefit. But of course, we brought it up to state-of-the-art technology with air traffic control equipment. New advances in cab glass, and brought everything up to the latest building codes.
That's amazing. And also like new aesthetics afterwards, right? Like the lights.
Oh yeah. The airport wanted to do a little bit more of a flair. So they had us design some sails, some stylistic sails on the sides of the building, which represents the city of Melbourne's city logo, which is sailboats. And they were also trimmed with LED lights that had controls that you could change them different colors.
Amazing.
Yeah.
This next question will be for both of you. I don't know if Alexis would like to go first. What were some limitations in designing the new ATCT, air traffic control tower, such as like budget, design, geometrics, or height?
Limitations as far as structural, we're pretty much constrained by the architectural design. So I think Brian can elaborate on that. Limitations for structural would be just the amount of columns that the cab consisted of. The cab was supported mainly on 4 columns. So that would be a structural limitation. But as far as dimensions, all of that is pre-coordinated, and we receive and have to work around those. So pretty much footprint and height. I believe the top of the tower is about 115, 120 feet high. So that's a limitation. But like I said, it all comes from the architectural design, the design concept. We don't set those.
Right.
Yeah. The architects always causing trouble for the structural engineers. But you mentioned budget. Budget's always a concern. The budget for this project was established early on during the site selection process, which took place a year before the design. And so that was based on previous similar structures, plus adding in a couple of years of inflation assumptions. So the successful bidder came in within our budget, and it was completed within budget. So working with the contractor, we kept it under $6 million.
Oh, wonderful. Continuing, did you have to consider any maintenance of the air traffic while choosing a new location or during construction, like the aircrafts? Yeah,
sure. Well, let's see. As far as the airspace goes, the airspace controls and classification of airspace in accordance with FAA criteria, that didn't change because the new tower is virtually or literally right next to the old tower. So the controllers had the same viewpoint of the airfield and the traffic in the air. So those things didn't change, but we did predetermine during the site selection process that the new tower was going to block the view of the existing tower during construction. So this was done through a 3D simulation that my company does for all these control towers. We simulate the whole airport, and we can move the tower around at any height and any location. So we put the proposed tower where it was proposed to be, only about 200 feet from the existing tower. And we could get a view from inside the existing tower to see what was going to be blocked. So part of the end of one runway was blocked, part of the approach was blocked, and then also some of the circling approach pattern was blocked. So we were able to identify that before construction, and the controllers had time to react to that and come up with some procedures to work around that, just temporarily during that 18-month period of construction.
Right. Great, that's very insightful. Well, I was going to add, so what was that simulation called?
Well, it's a simulation that we devised ourselves. We use a software called SketchUp, which is, I think, is produced by Google. I'm not sure if they still own that or if it was bought by somebody else. But it's very, very versatile, very easy to use, and it even when you import the terrain from Google Earth, it actually shows all the terrain features.
Oh. Nice. Yeah, I've used SketchUp for a project recently, actually. Very user-friendly.
Good, yeah.
And the next question will be for both of you, Alexis and Brian. What were some of the challenges you faced during the design of this project, and how were you able to resolve them?
Okay, I'll go first. First, I should describe more or less the different components of the tower. So the tower is pretty much it has about 3 different segments. If you think about it that way, it has the foundation, which is a huge mat foundation, which was 50 by 50 by 36 inches. So you're looking at a 50-foot by 50-foot square that's 36 inches thick. And the next component will be the walls. The walls are actually precast walls. So you're looking at kind of like putting together a Lego. So you have the foundation, and then you put together the precast walls, and then we work on the connections. That was one of the challenges, figuring out how many sleeves. So the connections between precast walls and cast in place foundations are done with sleeves in this case. I'll explain later what that means. And then the next piece would be the cab. So the cab is a structural steel section that is assembled at the shop and brought together and lifted with a crane. So the cab, the connection from the cab to the walls was a challenge. Detailing all these embedded plates that have to go on top of the walls to receive the cab structure. So locating all those plates, all those welds, that was a challenging. And the actual cab design itself with 4 columns was a challenge as well, because we had to line up and orient the roof framing so that it would only be supported on the 4 main structural columns. So there's a lot of detailing going on, a lot of different members, structural steel connections coming together at different angles. So you have to make sure that there's enough clearance to install the bolts, to weld, etc. So anytime you have structural steel detailing, it could get really complex. So and also I would say another one of the challenges was to just do all the preliminary checks that we do on structures, where we check if a structure is flexible, because this kind of structure is very slender. So it's more of a small footprint and very tall. Anytime you have a structure like that, you could run into like dynamic responses where you get more wind, more of a wind effect. So you have to check the period. You have to make sure that it behaves rigidly if it does, and if it doesn't, design for the increased winds. So those are challenges in the structure, I would say.
Awesome.
Okay, if I could add a couple things to that. Another challenge was determining what the FAA electronics and radar was to be supported to transfer from the old tower to the new tower. Were they going to just replace equipment? Were they going to relocate existing equipment? How much of it, how much space in the equipment rooms was going to be needed? What kind of wireways were going to be needed, especially in the vertical area from the top to bottom? So that was a lot of work. And another thing that Alexis can talk about is the cab glass design, or actually the whole cab design. Normally, we design a cab, and a lot of other people design control cabs of this size, 500 to 600 square feet, with 8 columns. We did this with 4 columns, and the reason for that was to improve visibility, and we were able to design what's called butt-glazed laminated glass. So we tried to make the cab as much of a fishbowl as we could, and so for the whole airfield, the controllers only had 1 column in front of them, and Alexis designed that as the smallest column at my request, and we had 3 slightly larger columns on the other sides. But Alexis, why don't you talk a little bit about that?
Initially, as Brian said, it's kind of like the shape of the cab is like an octagon. So you have 8 sides, and if you were to inscribe a square inside the octagon, you get 4 points touching. So those 4 points were the locations of the 4 columns that we used for structural. And one of them actually, as Brian mentioned, is smaller than the other 3 because that one required more visibility. So that was a special request, and due to that, we had to just basically work with those columns and make sure that, and it's not just, those columns are not only straight, they follow the shape of the cab. So we had to ensure that it was rigid enough and that we had complete joint penetration welds and all those different pieces of steel so that they would all come together as a single column. Because if you think of a column, you think of just a straight member. Well, these guys had the actual shape of the cab. So that was another challenge, and that generated very lots of different connections, rigid connections, moment connections. So applying the wind on that, as you know, that's on the top of the tower. So applying the wind on that, you have the highest pressures up there. So that was a challenge as well. There were other columns, but they weren't part of the main framing. As Brian said, we had 4 columns to work with, so we made them as small as we could to allow for visibility, and just checked all the limit states that we use for design. Check strength, check deflection, check shear, check moments, check everything, all the design checks that we do. And then work with the connections that we have to design for.
Yeah, and another special feature of that too, like Alexis was saying, it followed the shape of the cab, and that's vertical for the first 3 feet, and then it tilts out at 15 degrees, and then it goes up vertical again to the roof. And that 15 degrees is the height of the windows, which is 10 feet high. Yeah. And those columns had to be completely hollow, so we were able to run conduit through them for antennas and electrical cables through them. So Alexis had to be able to design welded connections of his beams to the sides of those columns so he wouldn't cut off any pathways.
Wow, that's very interesting. I love that. I love all that. Alexis, can you elaborate more on the structural system of the tower?
Yeah. As I was mentioning, as Brian just mentioned, the columns were hollow, so we provided, just to elaborate on that, we ran the conduits through the columns, so then we had to provide small openings at the base of the cab for the conduits and all the cables to come out from. So another concern was that since we had only 4 columns and now we were creating openings in them, that we would lose stiffness, that the cab wouldn't be as rigid as it needed to be. So we had to reinforce with plates and make up for that stiffness that we lost due to the openings that we generated on that. So thank you for bringing that up, Brian. I had forgotten about that. So Back to your question, as I was mentioning, it has about 3 or 4 different components. The foundation is a shallow foundation, so it's a 50-foot by 50-foot mat, which is just it's like a huge isolated footing by 36 inches thick, and it had dowels waiting to receive the precast panels, which are connected to the mat with these connectors called seals, which is a type of connector that comes precast in the panel, and the panels sort of like join the dowels, and then grout is placed in them. So our job was to determine how many connectors would be needed, because we had to be in constant contact and communication with the precaster, and as well as review their shop drawings, because these towers, lots of these components that are precast are not actually designed by us. They're designed by the precaster. So when it came to the walls, outside walls and inside walls, and also the floor system, all of those components are like small pieces that come to the site, and everything's assembled together. So these walls, these exterior walls, come with corbels. So at each level, it sort of has like a small concrete ledge, like a corbel around it, waiting for the floor system to come. So all these pieces as well have connectors. So you have to think about like walls that are about 5-6 feet long that are tied together with embedded plates. And when you weld them or connect them, then you get a continuous wall that goes around the perimeter of the tower. So the walls, the floor system, all these parts came from the precaster. So that covers the walls, the floor system, then the cab. The cab is, as I was mentioning, one of the more complex parts of the tower, because you have a lot of different shapes. Like the columns were HSS, which are hollow structural steel sections. The roof framing is composed of I-beams. So you have a lot of wide flange beams coming together into steel sections, and you have a lot of angles to stiffen up. You have a lot of cross bracing at the top level and below and right at the cab level as well. So the cab is pretty complex. I don't know if Monique could share some pictures that Brian provided to us at some point. When you guys edit this out, you could share some pictures so that it would be nice to look at. The cab is a structure, but it's pretty aesthetic to look at. Especially those pictures that show the crane lifting the cab. That would be nice to see. So you guys can see what's really behind what's the skeleton of the cab itself. That would be nice to look at. So it's pretty much those parts: the foundation, walls, and floor system for 7 levels, and then the structural steel cab that goes on top. That's what the structural framing consists of. Oh, I could add that the floor system, initially we went with a hollow core. We were thinking of using a hollow core system, which is it's very small, very light. It comes with precast. It comes precast from the shop, and it's stressed with tendons, with strands. So we were thinking initially of going with that system, but at some point, I believe the precaster offered another option to use just an in-house design of pre-stressed tendons, composite with a slab. And since the weight was similar, we okayed that, and we went ahead and framed the floors with that system. So in the end, we did like an equivalent of a hollow core system. You can Google what that means. It's a very typical system. It's a precast, pre-stressed one-way system. So since we had a small span for the main part of the floor, I believe it was around 13, 14 feet, it made sense to go with precast.
Okay.
So that pretty much covers the framing for the tower, I would say.
Wonderful. Thank you so much, Alexis.
By the way, I will be sharing the pictures. I will be sharing them once I edit the video and while we're all talking. I don't know them right now, but just FYI.
That's okay.
Awesome.
Perfect.
Yeah. Brian, what would was there an optimal location for the structure for the construction area for the tower?
Yeah, yes, there was. I mentioned before we did that 3D simulation,
Right.
and the FAA has what they call the FAA Safety Management System, and it's applied to practically everything that they build on an airport, everything that is built on an airport. Every project goes through this, and there's a special one called a Safety Risk Management Document to site control towers.
Okay.
So we started off with a number of different locations all over the airport, somewhere around 8 or 9. And through that process, that siting process, we whittled it down to 3 sites that were looked into in depth. And so we didn't just plop it down next to the existing tower because we thought that was such a great location. If it worked once, it'll work again. That frequently happens, but you still have to go through the safety management process. So we had a couple others on different parts of the airport, but lo and behold, this one won out as far as location, line of sight, height, utilities locations, and closeness to the electrical vault. So we had a panel of about 30 FAA and FDOT experts come in one day, and we spent 8 hours going through all of the different criteria and looking at all 3 sites, and we got a consensus from everybody at the end of the day to build it where it was at. So it is, without a doubt, the best location.
Awesome. I know Monique, she had a question about the FAA. I don't know if you would like to ask that.
Well, I just wanted maybe for you to let us know what it stands for, just because I know it's been mentioned a lot in the interview.
What is?
The FAA.
Oh, I'm sorry, Federal Aviation Administration.
Okay, perfect. And then I do have another question. So you mentioned that you were while you were building or during the construction process of this tower, the other one was obviously functioning, but so what happened between that period when you didn't have that existing one and you were like moving this one towards the locate? Like, is there no flights going on or?
Oh, no, the airport never shuts down. So at this airport, they do close the tower at night because there isn't enough traffic. You'd have to be like Dallas Fort Worth or Philadelphia International, something like that, to be running 24/7, or even Orlando I believe is 24/7. And in those cases, the way they transfer from an old tower to the new tower is they'll have a duplicate set of equipment set up temporarily in one tower over the other. So if they're putting in new equipment, they'll put up the new equipment in the new tower, but they'll replace it. I'm sorry. If they're going to transfer equipment, they will take some temporary equipment and put it in the old tower and transfer whatever they're going to transfer to the new tower. If it's all going to be new equipment, then it's a no-brainer because everything's by itself. It's separate. It's autonomous, and the cutover is easy. In our case, we had about an 8-hour period overnight to do some logistics of things that had to actually be moved from one building to the other. So that happens quite often. Most of the time, it's 75% of the equipment is new because these towers, like this thing, is over 50 years old. Even though they have upgraded equipment over the years, the stuff they had in there was still relatively old. So we had that 8-hour period to transfer anything that was not going to be new. We also used that time to coordinate with the FAA Air Route Traffic Control Center, because there's something called shout lines that go between facilities. It's kind of like like a hotline. You just pick up the phone and you get somebody else in the radar control center or another air traffic control facility. They have a hotline that goes to Patrick Air Force Base, for example. So those got transferred over during that 8-hour period. So everybody, literally working overnight. So that's how that happens.
That's very interesting. I didn't think about the time that there's an 8-hour time you have where no traffic is involved. I'm always thinking airports are 24/7, to be honest.
Yeah. Well, like I said, even the ones that have 24/7, they never shut down and moving to a new facility either.
Right. How many personnel will the new air traffic control tower support, and how would this load factor in the design for Alexis?
Okay. All right. So they have 2 shifts there, and each shift has 4 controllers. They'll have a supervisor, 2 local controllers, which are the guys that are watching stuff up in the air, and 1 ground controller. The reason for two local or air controllers is because of different runway use. So they've got a crosswind runway that is used primarily by FIT, and then they've got the 2 main runways that going in a different direction that handles all the other traffic. So if they've got both facilities going, like if FIT's got a lot of, Florida Institute of Technology has a lot of air traffic training with their flight school, they'll be operating the 2 local positions in addition to the supervisor and the ground controller. So there's a shift change, of course. So, you know, there's potential for 8 people to be in the building at one time as far as controllers go. And then it could be potential for another 4 to 6 people, either visitors or maintenance crew. So, you know, you could have a dozen, maybe 15 people at one time, which would be a maximum load, which virtually never happens, but it could.
Right. So it's not.
Yeah.
It's
and
like,
then the only thing that really that's affected in the building design by occupant load in this case is the fire ratings. And so I think you were going to ask something about exits, so I'll throw that in here now too, is FAA has a standard that if you have under 25 personnel in the building at any one time, then you don't have to have a separate fire escape. You have what's called a pressurized stairwell. So the doors in the stairwell are all sealed off, and there's a big fan that's usually placed at the bottom of the stairway, and there's an exhaust louver at the top that's all electrically controlled. When the fire alarm goes off, that thing kicks on and keeps that stairwell pressurized so that people can run into that stairwell and get out of the building, and it keeps smoke and fire out of it.
Amazing. Yeah, that was a very interesting question I wanted to ask. Thank you for answering that. How long will the life of the design last, considering the existing air traffic control tower is obsolete after 50 years?
Okay.
Like the last one was obsolete 50 years, so the new one, how long will it last?
Yeah, good question. The guideline or code requirements typically say a 20-year design, but in reality, in practicality, this will last at least another 50 years. It'll be here at least that long. If the other one lasted 50 years, the way it was built, compared to the way this one's built, I'm going to bet 100 years.
Wow.
Nice.
It's not going anywhere.
Right. We read that you were a licensed private pilot. How does the love of aviation complement your engineering specialty?
Okay. Well, my airport work experience actually came first.
Okay.
And it actually made it easier to become a pilot because I knew all the, runway markings and the lighting standards and radio controls and all that kind of stuff, because that's what you design when you're designing an airport. Because before I started designing control towers, I was a general airport engineer. I designed runways and taxiways and the airport lighting and drainage and all that stuff. I'm a civil engineer, by education. Right. So I actually made, my understanding of airports was good enough that I was able to apply that to being a pilot. So that was kind of handy. I learned things quickly. However, being a pilot has increased my appreciation of FAA's planning and design objectives, because having used the system, I've learned stuff that, I wouldn't learn designing. Now I actually know what some of these things are for, what's behind the design.
Right.
And then before I started designing towers, I was a general consultant to 15 Florida airports, and flying made it very easy to visit my clients. I could cover the whole state, anywhere in the state in a day and be home for supper.
Awesome. How often do you fly? Like, how often do you?
Well, since I started doing control towers, I'm working all over the country now, so I don't really fly that much.
Okay.
You know, back then I was flying 2 or 3 times a month, just for work.
Right.
So now it's more or less just for fun.
Awesome. Thank
That's
you for answering that.
I know we have one last question for both of you guys, but before that, I know we wanted to ask Alexis. So I wanted you to kind of speak about your experience in school, how like we know you have your bachelor's in civil engineering and then you got your master's in structural. So I know a lot of the students that come in here too, they're from FIU and they get very excited that you actually graduated from FIU and you got your master's from FIU. So I just wanted like your advice and kind of your experience of like, should they go right away once they graduate and get their master's, or should they work in between, or what do you think about that?
Well, I would say that my personal experience has been that it's really valuable to get design experience and work experience right after you finish your bachelor's. So I wouldn't recommend to go straight into the master's program, because you end up learning a lot of theory, a lot of more of testing and research based stuff, which is great. That's how we have our codes. Without research, without very precise analyses such as those, we wouldn't have our codes today. So we're very thankful for that. But if you go straight into your master's right after your bachelor's, you miss out on a lot of I would say skills that you gain only working and practicing as an engineer. So I would say that I graduated from my bachelor's in 2010, and I started my master's maybe a year later. And within that year, I feel like I gained a lot of experience. And I also did my master's working full time. I never took time off from work. So I would say that one thing complements the other. As you're getting more hands-on practice, it kind of strengthens your theory. So your theoretical background, which you're learning in your master's. In structural, you go into deep concepts, like in reinforced concrete, you learn how to design for torsion. You learn how to design for deep beams. There's a lot of special topics in structural design that you don't touch on during your bachelor's, and you do get a chance to strengthen or to go in depth in your master's. But if you don't have that practicality that you develop as you design as a practicing engineer, you kind of miss out on a lot. And also just the way you approach a problem when you work in practice in actual real projects, you tend to become very practical. Your approach, you simplify things. Because that's what we do as engineers. We get a complex system and we try to simplify it as much as possible with many constraints, such as how cost effective it is, how durable it is, what kind of serviceability it'll provide for its intended use. So there's many ways to frame a structure, but there's only a few that are actually efficient, that are cost effective, that are appealing, that the architect approves. So we're dealing with all these constraints. And I think if you just go straight, if you do 8 years of school or 6 years of school, I think now they have combined programs where you get your bachelor's and your master's. I think it's great. It's a great time saver, but I'm not sure it's the best thing to grow as a professional. I would say finish your bachelor's, get a strong base. You could do what I did. I took all my electives within my bachelor's in structural engineering. I took a bridge class. I took structural steel. I took reinforced concrete, masonry design, timber. So I took all the materials that maybe I got lucky and they were available. I'm not sure if these classes are available now. I took wind engineering because we're in South Florida. That's a major one. Mm-hmm. So I would advise just if you're going to go into structural, take all the electives you can in structural and then start, get hired by a firm and start working. Just being around an office environment, you'll hear discussions, you'll hear structural debates, you'll hear just a lot of cooperation, and you learn how to approach problems like that. So that would be my advice. And then once you finish your master's, you'll have a strong theoretical background, and you'll be, you'll be helped a lot. I mean, here in Eastern, it's been Riza, Gonzalo. Those are great PEs that have taught me all I know. So you pretty much, your knowledge is formed a lot, is influenced by them. So I would say that I wouldn't advise to go straight into the master's. If you want more of a solid background, I would say go start practicing, get a job, and start working. It really helps. That's my recommendation.
Right. Thank you so much. That's awesome.
No problem. My pleasure.
For both of you, I guess both of you could answer this final question. What was your favorite part of designing this control tower?
Well, let me go. I'll let you finish, Alexis. My favorite part was designing the control cab, designing the consoles, and working with the controllers and the FAA to decide, where the equipment was going to go, how that was going to be spread out among the 4 different controllers, because a lot of the equipment is the same from one position to the other, but some equipment is a little bit different from one controller to the other. And also have to pay attention to the view of the airfield to locate those positions correctly with relation to the layout of the runways. So that's always the most fun part for me.
Oh, that's awesome.
Yeah.
Yeah. For me, I would say it was the modeling, the structural modeling of the cab. That had a lot of complexities, just because as I've mentioned, we had to work with 4 columns, and that generated a lot of rigid connections and just modeling. We used a finite element method software called RISA 3D. So modeling that, it took a lot of tweaking of the boundary conditions of between whether supports would be pinned or fixed, and going back and forth and deciding what made sense and what would make for easy to build connections. And I would say that was the funnest part. We have all these tools that are great, but also these tools are very powerful and save you a lot of time, but checking whether the programs are running their calculations correctly, that's also interesting. In this case, there were a lot of different structural steel members. So doing those cross checks by hand, because you can never trust software, as you guys can imagine. So that was also that's also fun. Just double checking software to make sure that calculations are being done right, which is something we do for all our projects. But in this case, since it was such an intricate arrangement of members coming together, it was especially interesting in this case.
Wonderful. Thank you both for answering these questions.
Okay, guys, so I think
Thank you.
that's the end of our interview. Thank you so much for taking the time and answering this for us. Brian, if you're ever in the area, let us know. We'll buy you a coffee. David is going to be interning the whole time next semester, so he'll be here. And Alexis, I mean, we'll have coffee with you all semester long next semester.
Sure. My pleasure.
Thank you, David.
Thank you, Brian. Thank you, Alexis. Thank you, Monique.
Bye, guys. Have a good day.
Thank you for having me. Bye, everybody.
Bye, Brian.
Bye.
Bye.